How's it going, guys? It's Nick. I'm here to show you my final assembly of my final project. So my task was to fill the coffee cups with the coffee. Um, just to start off in the design first is this tank here. This tank would be where the coffee is coming from. The only thing that matters as far as dimension wise is the height from the top of this or the top of the water. I'm sorry, the top of the coffee level to the top of the cone, because that's going to affect the pressure, and the pressure was used to make calculations as far as the torque requirements. So I personally have it at 3 feet from. This is actually 2.5 feet because this is half a foot. So 2.5 feet by 3 by 2, that makes like 425 liters, which is plenty of uh, coffee, to store here. Some restraints or some set guidelines I made. The pressure inside here, it could either be closed or it could be open, but the pressure has to be zero here. Whether that's with a sensor if it's closed, some kind of pressure device, or if it's just open to the air. That pressure has to be zero. This height has to be from here to here has to be 3 feet. So yeah, that's the tank, and that's where the coffee is going to come from. It's going to flow through this PVC pipe. Um, these two things that are bluish looking, they're made out of aluminum. Um, yeah, they're not like moving, or they're not like, you know, they're important, but they're not moving pieces. So basically, they could be a lightweight metal. I did this to save money and save weight. Now I'm going to hide this mount. This whole blue thing is a mount, and it's just used to ground everything, and so everything's not free floating. It has something to rest on, so that to absorb vibrations and things, so as such. So let me go ahead and hide this and show you how this stuff operates. So the coffee would be coming through this PVC pipe, and when the timing is right and this is open, it will flow into this control volume, which is 37 ounces, and it's designed to, with this height, to have a flow rate exit velocity that's what I needed to fill this cup. So these two cams operate on separate cycles. So this one will be open for 3 seconds, while this one is closed for 2, and this one be closed for 2, and this one will be open for 3. I'm sorry, vice versa. Vice versa. This one will be open for 2, closed for 3, and this one will be open for 3, closed for 2. And while one's open, the other's closed. So they have whenever it's open, the hole will align with the PVC, and it'll allow flow into that controlled volume, and that's how we get the perfect amount to get into each can. And then when it's closed, it'll slide back. These spring systems on each followers are attached to the back of the actual mount, and they're aligned on a flat surface. They provide just enough force to push the mass of this with the acceleration to retract in enough time against this flow. And then the torque of the cam that's going to come from the motor and the gear ratio is enough to overcome the spring force, friction, and that's how I used that to find that calculation. So that, just to show you, this is how each one opens and closes. The hole will align open, and then it's closed. The spring is designed to resist and also push the follower back. Same thing down here. It looks a little bit off, but the cone does have some volume. The whole aligns perfectly. All right, so the next thing I want to show you is, so that's how the cam and followers work. I want to show you just very quick how I did the math. So this is all the Bernoulli's equation stuff. That's how I used what I used to find the force of the liquid on top of the cone, because that force would be from the pressure divided by or times the area. And that force would be needed to find a normal force to find how much friction will be resisting the translation of the follower. So here's the actual follower I listed as cam, and the forces on the follower. You got friction, the spring, the normal pressure force, and then the force of the cam required to make it move. So I summed all the forces and set it equal to what I want the movement to be, or the force of the movement to be. And that's how I found the force that's required for the cam. I multiplied that force by the pitch radius of the cam. That's the max distance torque arm. and I got 4,661 ounce inches when it's all said and converted. Here, I put the gear ratio as 10.1, but as you can see, this was a previous iteration. I forgot to update it, but the actual gear ratio came out to be exactly like 10.99, which rounds up to 11. And it produced an RPM of like 16. It's around 16. But I went ahead, and since we had a little RPM to spare, I went ahead and added a safety factor and made the actual gear ratio 11.5 instead of 11. And then here's the same analysis on the smaller follower. This one doesn't require much torque at all, 109.8 ounce inches, which is literally less than a third of what the actual motor provides. So there's no gear ratio needed for that. So if we go back to the SolidWorks model, I'm going to hide this motor. We're going to talk about that in a second. So yeah, this is the input gear right here. You can see my gears are operating properly. And then also zoom out, you can see that this is rigidly connected to the actual cam itself. This is the gear 5. The other gear is in there. But yeah, the gears are designed to maximize torque. And yeah, you can see from a top view, they're grounded. Is how it's connected to the gear. And then the motor, same thing down here. Like I said, directly connected to the motor. There's no need for gears to increase torque. The torque's already enough. The way the motors would be attached to this gear and the cam, it would be directly on the shaft, and it would just be keyed off at the end. The fact that it would be directly connected to the shaft will reduce like any losses in vibration and extra components. So let me pop the motor and the mount back up, and we could talk about why I chose them and the materials as well. So as you can see, the motors fall in 2 little slots. Ideally, these would be more snug. I just didn't want to, if I made it too tight, you couldn't see as good, but they're filleted. So like it fits in smoother. But you want these fairly snug to the motors in 2 different spots, because there's going to be some twisting motion by the motors, because they're going to be because of that torque. And so each motor has 2 locations where it's attached to the mount. You can also pull that out. You would have to take all this off at the top, but still not that big of a deal. It's not that complex of a design. The cam's resting on the mount, and the gears and the cam are resting on this mount. Also, you can see in some form the followers are guided by the mount or the cone, so that they're not, they move perfectly each time, and you have the spring resistance. Over here, this is a support. This is made out of steel. This is going to be directly connected to the mount, because as you see, it hangs out and there's weight, pretty heavy weight over here. This is a pretty big follower and pretty big gears. We need some rigidity and to reduce, the forces of vibrations and things like that, and make it more sturdy. So I added this out here, and then I modeled the conveyor belt and the can relevant to the measurements we came up with in class. So yes, that's how I designed this. Also, the cone, the height, size of this cone is designed to be control volume, 37 ounces exactly. It has a certain diameter hole and height to make sure I get that flow rate, which I also used a faster flow rate than what's actually necessary to fill the can in 2 seconds, because to accommodate for that rise and fall when it's opening and closing. So you're not going to get, that perfect flow rate throughout the whole period. So I had to use a slightly faster flow rate. Just to pick up on time here, here's my bigger cam, the one that's ratioed. We have small rise and beta angles, and you can see that directly impacts the actual velocity and acceleration. There's kind of big jumps from 42 to negative 42 in the opposite direction. That could become problematic, but it would have to be analyzed. The only way to reduce that is to increase my rise and fall time, because you see the jerk, the max jerk and velocity all occur at the same time. But I don't think it's bad. I just think it would be ideally be reworked to be a little more smoother. And same thing applies to the smaller cam too, because they're opposite and equal in timing. But the first one is a modified trap. This is a modified sine. So you'll see the difference in the acceleration here, the way it looks. But as you can see, the drastic changes in the velocity and acceleration and jerk all occur at the same time. But yeah, that's how I found out the cam sizing and all that, using these Excel documents. And yeah, from that, I was able to create this design. I already showed you the gears, how everything operates. I think it's pretty minimalistic. It saves space. As far as width goes, I only took up 2 feet of the 8 feet conveyor belt. So yeah, that was the whole goal of this. And then last thing I want to discuss is with this design, since it has 2 cams, it has a naturally built-in safety factor because one of these is open while the other one's closed. So say the power goes out and this one's open, only the amount that's dispensed into the can will come out because this is going to be closed, or vice versa. If this one's closed and this one's open, it's only going to fill that and then it's going to stop flow. So there's never going to be leakage onto the conveyor belt or onto the floor. This is technically like naturally controlled system if the power goes out, and that's just like a bad case. I don't know. Just something I thought about. Thought it was interesting to mention. But yeah, if y'all have any questions, be sure to leave them in the discussion board, I guess, and I would love to cover them.